Welcome back to video number 3 of my final project presentation. We are now on part 5 of the project, redesigning the LSTM neural network to see if results can be improved. I started the redesign by thinking back to part 4, where the testing results were good as shown on the left picture, but the forecast was not as shown on the right. I redesigned the LSTM neural network to improve performance by adding 2 layers, one LSTM and one dropout. The number of neurons for all 4 LSTM layers remains at 50, and the 3 dropout layers continue to have 20% dropout. Here's another view of the redesigned model, and here's a view of the layers from the Jupyter Notebook code. There's 8 layers total, counting the fully connected dense layer. I also identified the core parameters with items highlighted on this picture that were changed. I am now using 20% of the data for testing, added 1 LSTM layer, added 1 dropout layer, changed the training batches to 30, reduced the number of epochs for training from 100 to 50, and changed the number of epochs for forecasting from 50 to 30. Then I went to the Jupyter Notebook and created a new file. All the steps are the same, except for a few redesigned areas that I'll walk through. The first change was splitting the data set, because now I want to use 20% instead of 10% for testing. This provides a value of 251.6 rounding to 252. Here's what's going on with the data set behind the scenes. That also means the split index moved to 1006 and showing the first and last records of training and the first and last records of test show the split. This identifies the splits are where they were expected. The changes are also seen when checking the length of the normalized training data. The length is now at 1006 with a range from 0 to 1005, and that matches the 80% of training data as indicated from splitting the original data set. And here's another change for the training batch size, now at 30, because taking the 1006 data points, then moving them back 60 places is 946. Then dividing that by 32 samples is 29.6. That rounds to 30 for the training batches. Here's where the 1 LSTM layer and 1 dropout layers were added. Now I'm up to 8 layers. Another change was adjusting the training epochs from 100 to 50. Here's that change, and here's where I first had the epochs remaining at 100, but after changing the parameters, I had to make this change because the model would stall and the kernel would die. The updated result is displayed. The loss value was at 0.1188 at the first epoch, then decreased sharply to 0.0169 at the second epoch, with overall decreasing loss values remaining near 0 through epoch 50. Overall, this is a good result. Next, we see the updates for testing now showing 252 data points, representing 20% of the data set. Flattening the array means I adjusted the indices with the new values of 1006 and 1258. And displaying the prediction data frame shows 252 rows and 1 column. Here's the updated close versus prediction graph from training, and it's not looking great. Here's another view, and the prediction is bottoming out around $30 for a few months, then catches up to provide a good prediction later in the year. Here's where I updated the forecasting epochs from 50 to 30. This took some trial and error because I didn't plan on changing this, but the kernel was dying. Changing to 30 epochs here worked. More changes are seen when plotting the forecast graphs, especially when viewing the combined graph. Here's the last two graphs. The forecast shows a smooth line around $40 for data points in 2021 compared to a variety of actual closing prices, averaging $56. We are now at part 6, comparing network performance of the LSTM versus the redesigned LSTM. There is overall improvement with the redesigned network for predicting the forecast of the future year of 2021. The LSTM's forecast dips down and back up to around $22. The redesigned LSTM has a smoother forecasted line at $40, which is 2 times better. Both networks do have challenges identifying the stock price at a finer level of detail, but the overall yearly average in the redesigned LSTM has improvement. That improvement is due to adding the 1 LSTM layer and the 1 dropout layer. The extra dropout layer helps to mitigate bias and make better predictions. This also forces the network to work harder to learn. As more layers are added, the network makes better predictions. For training, the first LSTM model had 100 epochs, and the revised model had 50 epochs. Reducing the epochs made processing the model faster and produces the same general loss results. Reducing the epochs had little impact on the model's capability to maintain the loss. During testing, I was most surprised by comparing the results. In the redesigned model, doubling the amount of data for testing from 10% to 20% appears to have caused strange results. The original model has a very accurate capability of identifying the stock close price, but the redesigned model only does well for predicting the later dates in the year. We are now at the conclusions part of this presentation, and this includes what I learned from the simple RNN and LSTM models and the overall project conclusions. There are several things that I learned from the simple RNN and LSTM models. There's a big structural difference between both. The simple RNN provides a straightforward model that has some computing power but limited memory. The LSTM has advantages because it has the cell state to maintain the gradient and gates to identify what the network should keep or drop. Another concept I learned while thinking about the big picture and while waiting for my epochs to process is that a relatively small amount of programming is needed with both models, but there is a lot of planning. I also learned the big difference in time to process the simple RNN versus the LSTM models. The simple RNN processes relatively quickly, but the LSTM takes a lot of time to build and run. I also learned in the LSTM the number of training epochs could be reduced with minimal impact on the model's capability to make predictions. Overall, I found it fascinating that building models is not always the perfect fit the first time, but it is very much data science in action. And it feels like going to a virtual laboratory to create a model, evaluate it, and experiment with the results to solve a problem. For overall project conclusions, there are good use cases for the simple RNN and for the LSTM. It's important to understand how both models function to be able to apply the right solution to the problem being solved. It's like having a variety of tools in a toolbox to use for different scenarios and knowing when to use which tool to get the best results. Here's a few reference links for images that I used in my presentation. All right, everyone, that brings us to the end of this video. Again, my name is Elizabeth Jones, and this is my final project presentation for ADTA 5560, Recurrent Neural Networks for Sequence Data for the Fall 2022 session. Thank you for watching my presentation.